I am so proud of that. My gosh, I would. You're as racist. That is that's the question. That was weird. And he did that. You just need to. So, okay, you either make all the questions yourself. And then I'm like, really? I'm not sad. I got it. So that. Yeah, I get like a 95. Cool. Really? Because
good morning. I have your exams. I will call your names by last name alphabetically, so that you have an idea of when your name comes. So, Caitlin Dodd, Paul Glazier, Ian Calhoun, Dees, Zachary Edwards, Hannah Cavan. Marissa Holmes, Charlotte Cathy, Egan McKellar, Drew Kibler, Amanda Kitchens, Isai Monte, Laura Robbie, Mariana Sanchez, Greg Serengli, Sanders Siri, Wyatt Smith, and Wyatt. Matthew Snow, Matthew, Sandra Stehley, Nicholas Stores, Mo Wells, Hannah Ward.
You're really close. You almost had it. You're good. Oh, no.
Dragon Witt, Sadie Zimmerman,
Raven, just right now. Yep. Sorry. Sure.
So the grades you see on D2L as of now, there are two summarized grades you should see. One is final calculated grade and the other is final adjusted grade. Final calculated grade is what the formula adds up and gives, and final adjusted grade is what I adjusted with. So basically I return back 20% of the points that you lost. So if you've got 90 out of 100, so you lost 10 points, so I do back 20% of that, that's 2 points. So if it is 90, that should become 92. I also changed it a little bit in the sense that exams are out of 45 at this moment. I changed it to 60. That's just so that you have a true representation of your grades. Otherwise, later on, it gets diluted and there is a sudden spike in your or sudden dip in your grades. So just to avoid that, I dilute it a little bit. So here are the summary of your grades. So as far as midterm 2 goes, the high was 60 out of 60. That's full points. That's 2 of the students got that. Average is 64%. 80 to 100. There were 6 students. 60 to 80. There were 7 students. 7. There are 24 students in the class. This is after the curve. So this leads to a final calculated grade, and that after you curve, and for that there is a parameter A that I decide on. That's chosen to be 0.20, which means 20% of what you have lost. You also need to have a good score in the quizzes so that you get full points for that. By now, hopefully, you've understood that. So this is the total after everything. So the high here is reasonably close to 100. Average is 72%, and 90 to 100, 6, 80 to 90, that's 3, 70 to 80, 4, and 60 to 70, 6, less than 60, it's 5. So that's the distribution relative to what I have seen typically in these courses last year. The distribution is more towards the bottom, but I don't know what exactly the reason is. It could be the number of people who come to the class. It's again a different scenario that usually there are more number of students, not too many, but still it's not this low. But that's what it is. And any questions or comments on that? This is a reasonably good representation of what you might get as your final grade. The idea is if you keep doing what you're doing, you should be able to keep your score. That we have finished 2 quarters, there are 2 more quarters, and which will be reasonably identical. The concepts get as in any subject, it gets harder and harder as we go deeper and deeper into it. But then I compensate that by I will challenge less. So that will be the difference. The questions will be by challenging less means I will ask more like homework like questions. I'll try to deviate more from the, deviate less from the homework like questions. So that's what you can expect in the course. Okay. The homework 7, that's due. March 1, it's Monday. And midterm 3. So there will be homework, a couple of, or 2 or 3 more homeworks in between the last midterm. No. We started talking about magnetic field, how exactly you can create magnetic field. Remember, this is pretty much roughly a repetition or very closely related to the idea of electric field and how electric field was created and how electric field exerts a force on its source. There we said that we have charges. So charges, which is Q, that creates an electric field. And we use Coulomb's law for that. So that's E electric field. If it was a simple point charge, we said this is 1 over 4 pi epsilon naught times that is charge Q, that's your source, and R squared. And that is R hat. And this is just a symbol telling you what is the direction of the electric field associated with the charge Q. But the main idea is if you have a charge Q, it creates an electric field around it. So that's usually represented by lines coming out of a point charge. And this double arrow means that it is the opposite also. If you have an electric field, then it will exert a force on this charge. So that's it's a cyclic process. A charge creates an electric field, and that electric field will exert a force on another charge. So it's cyclic in the sense that there are 2 charges that are interacting through an electric field. So that's the basic idea. Here now, we talk about moving charges instead of charges. Or you can also say this is current. And there is a flux of charges, or there is a lot of charges moving one after the other, then you call it a current. So moving charges, so that's Q times the motion itself, which is given by the velocity V, and that creates a magnetic field. Oh, I should move this. So exactly like charges are associated to electric field, moving charges, charge times its velocity, creates a magnetic field, which we represent by the letter B. And now instead of the electric property of the material, or in this case the vacuum itself that comes into picture, here we have the magnetic property of the medium that comes into picture, which is in most often we are working in the vacuum, that is empty space, and this is the property of the empty space itself, right? The magnetic property of the empty space itself, which we call is the permeability of our vacuum. And this time instead of Q, we have Q times V, that's your source, and divided by R squared. And the direction, even though this is now a vector, it is not directly proportional to that. Instead, it depends on the radial vector also. So it depends on your R hat also. So that's 2 vectors. And this is given by the right hand rule. So this is a cross product between 2 when you multiply two vectors, there are two ways to do it. One is a scalar product and another is a vector product. So this is the vector product between the vector connecting the observation point and the source point and the velocity itself, and that's given by the right hand rule. So this here direction is given by the right hand rule. And that's broadly the summary of what we are doing. But as we did in the case of electric cases, some special configurations are relatively easy to deal with. And the easiest we worked with was finite. Wire. Finite straight line. And that was, you have a finite length of wire carrying a current I. Maybe I should have pointed out here that either I can talk in terms of moving charge, means charge times velocity, or I wrote down here that it is also current, also represents the same thing. So it is, if you're dealing with current, then it is I times length L of the wire. And what do you mean by a direction for a stretch of wire? If there is a wire, there is a current passing through it in the context we are talking about, and the direction of this length is associated to the direction of the current in there. So in this stretch of wire, the direction of L will be in the direction of the current there, and length of the wire, the magnitude of that will be the length itself, which is the usual intuitive picture we have. What we do is we want to know what is the magnetic field here. So that's your observation point. And draw a straight line perpendicular such that the line connecting them is perpendicular to that. And the magnetic field is given by this mu naught over 4 pi. It depends on the current I, and this length here, let's call it R. Sometimes it's called R, some other places it will be called the distance A, whatever you represent this length with, that's your R. And it also depends on where this point is. Now, the position of this point relative to this wire comes into picture. Is it right at the center of the wire? Is it at one corner, or is it very far away? So that observation point plays a role, because how far it is from the wire matters. And if it is the same distance, but it could be very far away, that should be weaker. And that's taken care of by the angles, sine of θ1 and sine of θ2. Here, angles are measured in the following way. You say this is θ1. And that's your θ2. Notice that I have given arrows to these angles. That means that in the directions I have shown, that's where you will measure positive. By any chance, if this angle was measured in the opposite sense, then it should be a negative. For example, if you have a scenario where that's your length of the wire and your observation point is here. And in that case, you will stretch. Imagine this straight line to be going all the way, and the perpendicular distance will be here. So that's your position R. And now your angles will be both in this direction. So that's your θ1. And that's θ2. θ1 is in the same direction as we picturized here, but θ2 is in the opposite sense. So this will be a negative angle. And sine of a negative angle is basically negative of the sine of the angle. So often, sometimes, be careful with which formula you're using. This formula is often sometimes written as sine of theta 1 minus sine of theta 2. That's also perfectly fine, but just make sure what is the sense in which you are measuring the angles. That is the only difference that comes in. We extended this formula for the special case when this is infinitely long. And in that case, you have theta 1 becomes pi over 2, theta 2 becomes pi over 2. When it is infinitely long, this point goes all the way to the bottom here, and that will practically mean that this line is being moved to the right as much as we can, and that would mean that that becomes pi over 2. Another simple scenario you can consider with that is so another simple scenario could be half wire by half wire. That's just a name I created. It may not be a standard name here. What I mean by that is that you have a point here, which is the end of this wire, but at the bottom, this goes all the way to infinity. These three dots mean that this wire extends to the bottom, but this comes and stops here. Or we are talking about the contribution of the wire starting from infinity and reaching here, and here it might take a bend. So it might move somewhere else from there. And we could ask, what is the observation point or what is the magnetic field right at the point shown? So that's your observation point. And in this case, I was demonstrating how you measure the angles now. So one corner is here, right? So that's theta 1 equal to 0. So that's theta, or that's theta 2, right? Theta 2 is equal to 0 because it's pretty much identical to the line itself. And here, the second end of the wire, you go all the way down. So this is pretty much parallel to that. So that's your theta 1, which is pi over 2. And you can see that the magnetic field then is equal to mu naught over 4 pi. So let me say this is the magnitude. Here also I should say this is the magnitude. I'll come back to the direction there. And again, current I in the wire, the distance R, and this time sine of theta 1, which is sine of pi over 2, plus sine of 0. Sine of 0 is 0, so that's 0, and that's 1. So 1 plus 0 is 1. So this is mu naught over 4 pi times I over R. It is good to realize that this is exactly half the magnetic field that you would have got if it was a completely, if this wire was extending from minus infinity to plus infinity. So it is good to write this as 1 by 2 times mu naught over 2 pi times I over R. That means that this is the magnetic field due to the complete wire going from minus infinity to plus infinity, and it is a half of that. What about the direction? Direction, always you hold the wire with your right hand and hold it in such a way. There are two ways of holding it, if you notice. Either you can point the thumb in the direction of the current, align it, or you can align it in the opposite direction, and the curve of your fingers. So when you're holding it, there is a circular nature of your fingers with the end of your fingers forming the arrow, and you will notice that there is a circle there. So the circular part of the magnetic field will be like this. So that's coming from the back. That's your magnetic field direction. So in that sense, if you were to extend it here, here it is going in and it is coming out on the left. So if I were to show that for this particular wire, all the magnetic field lines will be going in on the right side of the wire. And it extends further out. And then as you get farther, it gets weaker. It's coming out of the board on the left side. So these are circles, right? It goes in, makes a circular path, comes out, circular path, and so on. So magnetic field lines are circular, and when you get the circles are represented by your fingers when you hold the wire. And again, this is coming out on the left. And they get weaker as you go farther. So weaker means less dense lines. That means less dense lines means you have to show it a little farther as you go farther. And here it will be, these lines will be here. And they're again coming out of the left side and going into the right side. Same thing in here. It's going up here, so it should be going in here, and especially at this point, that's going into the page. So the magnetic field lines are going into the page on the for the problem that we are discussing. Here it comes up. So that's for a wire. We can extend this a little bit to do a square, and it is good to do a square because I noticed eventually we would like to talk about a circle. So think of a circular path. That's what we would like our wire to be. But to reach here, what we first do is let's think of a square that exactly touches the circle at 4 points. So, and let's talk about a current passing through that one. And the goal would be, so once you do the square, you again come back, and once you learn how to do the square, then you say that, okay, I'll make it 5-sided, 6-sided. So if I were to touch, I have a hexagon that is touching the circle at 6 points. And again, you can pass a current I through that. And here you will see that there's a 4-sided, so I'll call it n equal to 4. This is n equal to 6. Nothing special about 4 or 6. It was just easier to draw. And you can keep increasing the n and keep the restriction the same, that all the corners of this polygon should be touching the circle. And as you increase the n, you will notice that it approaches the circle as much close we can, and the limit n tends to infinity, it is expected to be an exact circle. So that gives us an idea of how we can think of generalizing to a circle from our formula for a straight wire. So we'll do that. First, let's do the square. Now that we know how to calculate this for one piece, now there are 4 pieces in here. So first, let's start with the side 1 here. That's the observation point. So be at center of a square shaped wire. Unlike what we did here, we are not calculating the magnetic field anywhere. We are talking about a specific point, which is the center of the square, and that center we imagine to be the center of the circle that the square touches at 4 points. This will be the radius r of the circle. Let's talk in terms of the length L of the circle here. So that's your length if this was 2L. So that's your length L, that's your length L, this is length L. And we are interested in the angles. It is clear that this will be 45 degrees. The total angle for the square is 90 degrees. So this is 45 degrees. And that's 45 degrees. those are the quantities we did, and there is a current I passing through this wire. So let's see what will be the magnetic field due to one side of the wire. Let's call this 1, 2, 3, and 4. Right, so that's 4 sides of the wire. So that's B1, the magnetic field due to the first side of the square. That's equal to mu naught over 4 pi times the current I that's passing through the wire. How far you are from here, so that's your length we are talking about. That's L and L, right? So the total is 2L. So this will be I over L. And sine of 45 degrees, sine of 45 degrees plus sine of 45 degrees because they're measured in the opposite directions. So sine of 45 plus sine of 45. Since we want to extend this further to higher number of sides, let's write this 45 degrees in a special way. So 45 degrees is pi over 4, and pi over 4 itself is multiplied by 2 and 2, so that's 2 pi over 8. So if you have the full circle represented by 2 pi, you divide it into 8, you get 45 degrees. So that's 2 times that. So that's mu naught over 4 pi times I over L, and this is sine of 2 pi over 2 times n, where n is equal to 4. So n represents the 4 sides of a square, and that's what that is. The contribution to this magnetic field is what's the direction of this. You hold this wire using your right hand, and now we are interested in the magnetic field at the center of the wire. And if you notice, when you're holding this, the fingers are coming out of the board right at the center. So it is coming out of the board. If it was somewhere here, it is going in. It is coming out of the board. So direction is out of board. What about B2? So that's for side 1. What about the magnitude of B2? There are 2 things you should worry. One is what's the magnitude itself? Is it any different from the first side? And the second one, is it still going to be coming out of the board, or is it going to cancel it out? And again, you see that, oh, hold it. And you notice that when you're holding it with the direction current going up, the fingers are still coming out of the board. So they are going to add up. So 1 and 2 add up. What about 3? That's still adding up because the fingers are coming out of the board when my thumb is pointing in the direction of the current. And the 4th one still is coming out. So all 4 of them add. The direction of all the magnetic field from each of the 4 sides is exactly the same. And before I proceed, I think I made a mistake here. There were 2 signs, right? This is sine of 45, 2 pi over 8. That's sine of 45, but there are 2 of them, so I should be multiplying by a 2 there. Right, so sorry about that. So that's 2, factor of 2 comes in there. Next, I was saying that B2, what will this be? Again, that is 45 degrees, right? That's 45 degrees, that's 45 degrees. And the same length, everything remains the same. B2 is exactly equal to B1 magnitude. And that's also going to be the same as B3. And it's going to be B4. Magnitude wise and direction wise also, it's exactly the same right at the center of the square. So the total magnetic field, so B total will be equal to 4 times B1. And 4 times P1 is exactly 8 that comes up. So that's 2 times n. So this mu naught over 4 pi times I over L, and then there is just 2 times or 2 times n, I write, and sine of 2 pi over 2n. This is basically 45 degrees, a way of writing 45 degrees. Instead of writing 45 degrees, you write 2 pi over 8, and then you realize that 8 is nothing but 2 times 4, and you represent n for 4, so that I can increase the number of sides right in this formula. Let me also split this 4 pi as 2 times 2 pi, so that this comes below here. So 4 pi I can write as 2 and a 2 pi here. And everything is coming out of the 4. This is equal to mu naught over 2 times I over L. And let me write this as, when I want to write this in the denominator, the 2 pi over n, so it will flip down, right? So let me say this is sine of x over x, because whatever shows up here, 2 pi over 2n and 2 pi over 2n, that's exactly the same. And what I mean here is x is 2 pi over 2n. That's your 45 degrees. A way of writing 45 degrees, I said x is 45 degrees, and that's all it is. And that's the reason why I write it in that form, because now when I do it for the hexagon, I don't have to do anything. It's just that I have to change the angles. For a hexagon, this will be exactly 2 pi over 2 times 6. If it is a heptagon, it is 2 pi over 2 times 7, and so on. It's only the angles that change, and the length accordingly will change, but it's only the length L that shows up. So it is it's just that L that we have to keep changing, and it is x over x that always comes in. What happens to x in the limit n becomes very large? That means to say that the number of sides of this polynomial increases. If this was very large, x is very small. And this means to say that we're talking about sine of a very small angle divided by that very small angle. In the very small sense, you almost want to make it 0. And if you were to do sine of 0 over 0 in your calculator, it will show a syntax error, right? So sine of 0 is 0, and x is also 0, so that's not very well defined. But if you were to actually do sine of 0.001, what you should do is sine of a small angle 0.001. First do this and then divide it by 0.001. And then you will notice that it is not exactly 0, it actually goes to 1. This quantity here in the limit n is large goes to 1. And this, the way you write this is n approaching infinity. That means n is getting very large. That's the way to write that. So that actually is equal to 1. As that increases, we also want to talk about what is this distance. So this remains the same. So that's your r. And the overall for a circle, the magnetic field for a circle becomes N. So let me summarize this. So B due to a circular wire will be equal to, again, you want to think of this as n is being very large. So n is large. same formula, but n is large. So this is so n is very large. It's what is your length L? It is for a single piece down here. So that's your triangle, and that's your length L. Right? How far you're from the center, how far is each of these wires? That's your wire, that's your current I. So how far is it? That's in the limit n goes very large, L approaches R. So this language is L approaches the radius R of the circle. And the other factor we said is sine of x over x approaches 1. And we can also say x itself, right? X is equal to 2 pi over 2n. And the limit n is large approaches 0. So a lot of things happening together, but the main idea is that sine of x is very small. X is also very small. A small number divided by a small number, it doesn't always have to be 0 or undefined. In this particular case, this is very well defined. It comes out to be 1 in the case when n is large. But what is the magnetic field? The magnitude of the magnetic field is, now in the case when sine x over x becomes 1, it becomes very simple. So that's mu naught times I times 2 times the radius of the circle. Right, that's the expression for the magnetic field due to a current carrying loop of wire. So this can be represented like this. So that's your current I. And we're talking about the center, right? At the center of the circle, what it is. And you again hold the wire, and anywhere you can hold, and you'll realize that the fingers are coming out. So that represents the B. The circle that represents at that point is coming out of the page, and that's your magnetic field. So direction is out of the page of the wire. So that's good. So this is due to a circular wire, but then you say that like we did about a straight wire, why should we actually close the loop? Can we leave the loop open? And what will be the difference in here? And this can be generalized very almost immediately. So let's talk about V to a circular arc. So what we are talking about is that there is imagine a circle, but the wire is not passing through the whole part of the circle. Instead, it only makes a small arc. So it starts from here and it ends there. And what is the characteristic of this arc? One is that it subtends an angle at the center. So that's angle theta. And of course, that is the radius r of the circle, that's r. And the magnitude of the magnetic field that's created at the center is pretty much the same, but now we have to bring in the angle theta. So that's 4 pi times I over r. That is, instead of 2, now I have a 4 pi, and you multiply by angle theta, but which has to be in radians. So the only restriction here is that theta has to be in radians. It's common for us to work in degrees, but in this formula, since it comes out completely separately, then you have to put it in radians. In the sine function also, often we write it in terms of radians, but then often you can you can set your calculator to work in degrees, which is often convenient in the way we talk and for the intuition purposes. So this theta is in radians. And remember that how is the arc length related to this angle theta, or what is the theta for the full circle? So theta is equal to 2 pi for full circle. For full circle. If you put in the angle theta equal to 2 pi and 4 pi cancels out to give you a factor of 2, and that immediately gives you the magnetic field formula for the circle. So this is a more general equation than a circular wire. The two formulas that you will often need for this course is that magnetic field due to a circular arc. This will be there in your equation sheet because this can come out of that, right? So this will be available in your equation sheet. And the other is the one which had a finite length of wire, the sine theta 1 plus sine theta 2. And most of the geometries I will build will be using circles or part circles and finite length of wire. I can combine them and talk about what will be the magnetic field. In your homework problem, you have a configuration where you have wires going like this. So there's a straight wire, then it takes a circular arc and then goes this way. So this part is a circle, like a quarter circle if you want. That's a straight line, that's a straight line. And you build circuits like that, and you can ask what is the magnetic field at a specific point around that. This is what I'll cover today. We'll come back and talk about how we can add this magnetic field when they are not in the same direction next time. Thank you.